Hi, grade 11s. We're on our days 8 and 9 for exponential functions. We're doing applications, so real life word problems. I don't think that you need 2 full days to work on these. However, you do need a little extra time to continue practicing your graphing of exponential functions and their transformations. So you make Monday, Tuesday, and Wednesday work for you, that you have all the homework done that you need to, and you've worked really hard. So let's do a few of these problems together. The first one, Greater Listowel had 7,100 people in 2010, and it has been increasing conservatively at 3% per year. Per A, that means per annum or per year. We often see percents written like that. How many people can council anticipate planning for in the year 2020? So if we have 7,100 people in 2010, and we increase by 3%. Let's figure out how many there are in 2011. So 3% as a decimal. That would tell me 3% of 7,100, which is 213 people. Oops, 2011. So then in 2011, we would have 7,313, and we would add another 3% to them. That would be 219.4 people. I don't know how you get 0.4 people. Don't point fingers at anybody. 219 people. So this would be for 2012. We would add that many, and so on. There's got to be a better way to do this. So we are going to use exponential functions to model this situation. Our rate of growth is to keep the 7,100 people and add 3% to it each year, adding 3% to the new total, and so on. So our rate of growth, which you would have noticed in course notes 80, is 1.03. So the 1 keeps the original 7,100, and the 3% adds 3% to it. If you have a rate of growth, your rate of growth is always larger than 1. You know from exponential functions, if you have a base that's larger than 1, you have growth. It's going to look like that. We don't want Listowel to get any smaller. So our rate of growth is 1.03. That's the base of our problem. And it's going to grow that way every year, more or less. But we have a vertical stretch factor 7,100. In other words, our y-intercept, which we know gets affected by that number, and our steepness factor is affected by the 7,100. So our population will be 7,100 times 1.03 to the power of x. This started in 2001. I'm just checking. 2010, I'm sorry. We want to know 10 years later what the population will be. So our exponent will be 10. Our population will be 7,100 times 1.03 to the 10, which is 9,541.8 people. 0.2 people, or 2 people. Approximately 9,542 people in 2020, which is an increase of 2,442 people. Mold is left to grow unchecked on the back of a large barn. If it is increasing by 50% per week, and you noticed it at the beginning of the summer at 9 inches squared. So maybe your little patch of mold was 3 by 3. Whatever, you could eyeball it and say it was 9 inches squared. How big an area will the mold cover if it continues growing as such for the 12 weeks of summer? So our rate of growth we need to think about is 50%. So we keep the original mold. This is maybe not something we want, but we keep the original mold and we add 50% to it every week. So our base of our equation is going to be 1 to keep the original mold and an increase of 50%. That is the base. My exponent it is increasing by 50% per week, number of weeks. And I have my original amount is 9. So what I am looking for is an area. So my area will be, start with the 9, 1.5 to the power of x. So in 12 weeks, the amount that I will have will be 9 times 1.5 to the power of 12. What size of an area will I have? It's 1167.7 square inches. Out of curiosity, how would we find that in square feet? We have 2 dimensions. We have the length and the width, and each of those at this moment is in inches. So if I wanted to convert this 3 inches and this 3 inches to feet, I would divide each of them by 12. So I would have 0.25 feet, 0.25 feet to get my area. I would have 2 dimensions. So I am going to divide 1167.7 divided by 12 twice. That's not the best form, but I'm going to do, because that sounds like an awful lot of mold to me. It is 8.1 square feet. That's like a 3 foot by 3 foot almost square. That's a fair bit of mold. That's really gross. Okay, next problem. What is the value of a Saturn that your mom bought, because your mom is cool, bought 6 years ago if she paid $27,500 for it, and it has been depreciating by 18.5% every year? What is the rate of increase? Oh, hold on a second. This one isn't increasing. It is decreasing. So we know that our graph is going to look like exponential decay. So we know that our rate of growth, if I can use that phrase, is a fraction. It is going to be less than 1. Our rate of growth is what you keep. So in the last problem, our rate of growth was 1.50. We keep the original amount of 9, and we also keep 50% of it added to it each time. This time, what we are keeping is not the 18.5%, but the remainder from 100. So if I do 100, subtract 18.5%, I get 81.5. That is the value of the car that you keep. That is my rate of growth, or my base. So 0.815 as a decimal to the x, where x is years. My original amount, 27,500, is my vertical stretch. So the value of the car, it is 27,500 times my rate of growth. We are left with, it's going to be sad for us Saturn owners, 5 to the power of, we wanted to know 6 years. It is only worth $8,000. $8,058.95 when I look at it in 6 years. In other words, if we have an amount, this could be different things like population, value, percent left, something like that, but amount seems to cover them all. Amount equals. We tend to use this notation for initial value or initial amount times your rate of growth. Oops, let's write that down here. And your x is your number of increases usually in time, not always. Remember your rate of growth. If it is in fact growth, your b value is greater than 1. We usually have 1 plus a percent. Sometimes you have doubling time though, and you just have a 2. Anything bigger than 1, you're going to have exponential growth. If it is exponential decay, then your base is less than 1. If you are losing a percent like we did in that problem just before, then you have 1 minus your percent depreciation. Let's look at one more problem. Radioactive radium-221 has a half-life, so they're not talking about a percent, of approximately 30 seconds. How much of a 300 milligram sample would be left after 5 minutes? So we want to know amount of radium. We start with 300, so that would be my initial value. I need a rate of growth here. My rate of growth is a decay because I have a half-life, so I have a certain amount of radium, then I have half, and then I have half, and then I have half, and so on. A half-life, the rate that I am changing is having it each time, and my x is time in 30-second intervals. It is important that we lay out what the exponent represents. Years, months, days, 30-second intervals. I want to know how much I have after 5 minutes. So how much do I have if I am having it constantly in 5 minutes? How many 5 minutes are there in 30 seconds? There are 10. Let's see what we're left with. 300 times a half to the power of 10. Decimal 03. So it disappeared very quickly. This was milligrams. Sorry, put an extra 0 in there. Decimal 3 milligrams in 5 minutes. Course Notes 95 to 99 has quite a few excellent word problems. Page 261, you have a selection there as well. So you've got 2 days to work on these and make sure that you can graph with transformations.